Welcome to the fourth tutorial of the climate modeling series. It's great to have you back. In the last tutorial, you built a model to describe the evolution of global mean surface temperature in response to energy imbalances. In the bonus section of the tutorial, you were asked to calculate the equilibrium climate sensitivity of our model. The equilibrium climate sensitivity tells us the long-term global warming caused by a doubling of CO2 above pre-industrial concentrations. However, the solution to that bonus coding exercise should have revealed that the equilibrium climate sensitivity of our model was much too low compared to more realistic climate models. One thing we can ask is, what are we missing? Well, one thing not well included in our models thus far is many of the internal climate feedbacks that work together with radiative forcings to define the response of the Earth system to energy imbalances. There are a variety of flavors of climate feedbacks, and we certainly cannot incorporate all of them into this model in such a short time frame. But in this tutorial, we will focus in on just one climate feedback, the ice albedo feedback. We'll do a brief description of it here. So while Earth's ocean are very dark and absorbent, ice and snow are bright and reflective. When Earth heats more, say to increase insolation or incoming solar radiation, more snow and ice melt. This makes Earth's surface less reflective, and therefore the albedo is lower. This allows more incoming radiation to be absorbed, causing Earth to heat up, and more ice and snow melt, and the albedo lowers again. The opposite is also true. When Earth gets colder, say from less insolation, more ice and snow form, making it more reflective, allowing less energy to be absorbed, and making Earth colder still. This is the essence of a feedback loop, and in this case, it's a positive one because the direction of change is amplified. That means that cold gets colder and hot gets hotter. A first approach to incorporating this into our model is to make albedo dependent on temperature. Up until this point, we have used a value that was determined from observations, but moving forward, we're going to be using a piecewise function depending on temperature. When Earth is very cold, say below 240 degrees Kelvin, like it could have been in the Neoproterozoic around 600 million years ago, we assume Earth is covered in ice, and thus the albedo can be unaffected by further decreases in temperature. Similarly, when Earth is warm, say above 300 Kelvin, like it could have been in the Eocene 55 million years ago, we assume that all the ice and snow have melted, and thus the albedo can decrease no further and is set at a constant value once more that reflects the very low albedo of an ice-free ocean and land. In between, we have this partially frozen state where the albedo can increase or decrease depending on temperature decreases and increases respectively. The shape of this curve is important, so note that for temperatures that are above but near our lower bound of 240 degrees Kelvin, the amount of absorbed shortwave radiation increases much faster than when we are approaching 300 degrees Kelvin. This is because the equator receives the most direct insolation, and it also takes up the most area per degree latitude on Earth. As it de-ices, the contribution to the absorbed shortwave radiation is thus very large. This is in contrast to when the Earth has warmed such that it's approaching 300 degrees Kelvin. This slower increase in the absorbed shortwave radiation as the temperature increases is attributed to losing the polar ice caps, which have the smallest area per degree latitude and receive the weakest annual insolation. We also note that the solar radiation that Earth receives is not constant in time, and this affects the energy budget of Earth. In this tutorial, you will explore how the equilibrium temperature responds to energy imbalances caused by this changing insolation, as well as the new ice albedo feedback we have incorporated into our model.